Hello, my name is Yourri-Samuel, and today I'm presenting on microstructures and engineering properties of high-strength continuous carbon nanotube yarns for structural composite applications. So to tell you about it myself, I went to Florida State University, where I studied carbon nanotube technology under the funding of the NASA STRI US Comp. I got my bachelor's from Winona State University in composite materials engineering, where I worked at Celanese in R&D. At the same time, I had joined SAMPE, which I'm actually coming up on my 10-year anniversary with. I am now with the Spaceship Company, where I'm a manufacturing, research, and development engineer. So today's presentation will go as follows. I'll introduce the topic of my dissertation work. I'll then cover three studies that comprise a majority of it, and then finally, I will make some concluding remarks. So first and foremost, what are carbon nanotubes and their materials? Well, in the early 90s, AGEMA found a material, carbon nanotubes, that demonstrated unrivaled strength to weight ratios and, of what we know, realistically on Earth, have the highest theoretical properties. Well, since its inception, many studies have occurred and benchmarks have been set, and as of recently, the newest benchmark exists. Carbon nanotubes bundles have been physically measured to have specific tensile strengths and modulus of 27 to 31 and 337 to 640 newtons per text, respectively. To put that in comparison, an IM7 carbon fiber, very standard product that's used heavily in the composites world, has a specific tensile strength and modulus of 3 and 90 newtons per text, respectively. If you're interested in what that material looked like, the TEM of that carbon nanotube bundle that's tested is on the right-hand side. Now, for today's presentation, a carbon nanotube bundle is actually one of the constituent parts that makes up my yarn. And let's actually see how that's done. But before we go any further, let's actually point out the differences. We want to replace carbon fiber, so what is different between a carbon fiber and a carbon nanotube material? Well, a carbon fiber is a monolithic continuous structure. That is, it's a continuous solid phase. As a load is applied, it is spread throughout its entire system. Whereas a carbon nanotube is made by an entangled network. Think of a big bowl of spaghetti. These carbon nanotube networks have to rely on entanglements between one another and van der Waals interactions to transfer these loads. You can see why that is when you take a look at the top right-hand side. The yarns I work with are made by taking an aerogel through FCCVD processing and spun into that yarn, so it's a little bit denser. So what were my research objectives and what exactly is the novelty behind this? Well, I'm going to go very deeply into each one of these, so let's just hit the generalized look of each study. First, I wanted to take a look at the morphological effects at length scales that are actually engineering worthy. We don't want to be looking strictly at lab scale targets, things like 20 millimeters. We actually want to do full scale tests because no other study had done it at this point. Two, if we're going to make a composite, it's prudent to take a look at not just the fiber system, but one of the other components. A very important one that's often overlooked, the interface. And that's done through surface chemistry. And lastly, by taking the knowledge gathered in the other two studies, I implemented it into a microcomposite study to try to create the best carbon nanotube yarn that I possibly could. So on the right-hand side is a small teaser. You will see 2 stars as well as the final goal. Those 2 stars are where the yarn started when I first had them, and then where they moved, and by the end I'll show you where they're closer to at this point in time. So first and foremost, the fiber-focused study. Carbon nanotubes show amazing mechanical properties, but at very short length scales. As you see on the right-hand side, we can obtain, this is actually a relatively old study as well, Newton per text up to 4 at 1 millimeter gauge lengths. Well, you can't make a rocket ship with 1 millimeter of yarn. And what we see is as we increase that length, our properties begin to decrease very quickly. Additionally, despite all these studies that exist, the ASTM that is meant to be followed for textile systems really hasn't been followed. It states test the short length scale as well as test the very long length scales. And no one had done that at this point. So let's quickly get through some of the bits that comprise the study before we see the actual results. I tested 3 different yarns, specifically Miralon yarns by Nanocomp Technologies, the first being a standard product that I chemically treated, which I call LCY. then a mechanically separated variation of it called the SCY, and then lastly a highly packed and collapsed variant called the flattened or FSCY. The motivation was to test how different cross-sections and packing effects would affect our final mechanical properties. We then did structural characterization through density and linear density measurements. To get cross-sections, we ion beam polished and then took it to an SEM. For degree of alignment, we did wide-angle X-ray diffraction. When we had our intensity data, we fit it to a Lorentz function to get our HOF, or Hermann's orientation factor. An HOF of near 1 gives us a very high degree of alignment, whereas an HOF of 0 gives us a complete random alignment. For mechanical testing, we did capstan testing instead of a standard, more traditional tabbed up, just direct pull. We found that this provided much more consistent results, and in this case, we preloaded all results, and then we stopped when max stress dropped below, or when stress dropped below 5% of the max peak stress. We tested 40 samples, and that data was taken and input into Minitab for right sensor parametric analysis. Now for the results. Morphological characterization. Well, we noticed that right away, if you take a look at the bottom pictures, that the FSCY was greatly densified, so we got improved packing as well as a significantly greater surface area. The SCY modification did increase our total surface area, as well as reduced our densities usually a little bit less, just a little bit more, just because of the fact that some of the voids were removed. However, it did come at the effect of increased surface damage. And lastly, the LCY did show some large voids that reduced its overall density. Now, degree of alignment. LCY and SCY show extremely similar degrees of alignment. However, we can then tell, because of the similar degrees of alignment, any changes in mechanical properties really aren't going to be an effect of between the two of them. However, if you remember, the FSCY was greatly packed, and previous studies showed packing is supposed to be a governing factor for strength. However, the densification process greatly reduced its alignment across. So we're looking at a center of approximately 45 and an edge around 30% alignment. And this actually makes quite a bit of sense. Flow of carbon nanotubes is used to align them all the time. It's a very popular technique. So when pressure was applied, instead we got flow outwards, reducing our overall degree of alignment. So when we take a look at mechanical properties in the next slide, you'll notice a trend. That is that very clearly alignment is the key factor of strength, because otherwise we would expect the packing to greatly improve it. Next, we notice an S-tail phenomena, likely due to the fact that the packing isn't as great in the other two systems, the LCY and the SCY. It's very distinct in the LCY, which has a lot of voids. So what we get is actually a strain hardening effect, even with a preload. A great amount of preload needs to be applied to remove this, and this will actually come later in the final study. Let's take a look at the mechanical properties distributed, though. The LCY and the SCY exhibit very similar property, with the LCY having slightly less overall variation, which makes sense. It's a standard product. The FSCY showed very poor properties despite the improved CNT packing. However, each carbon nanotube variation is still technically weaker than carbon fiber. But we'll address that by the end. Analysis of failure modes. In addition to just purely looking at the numbers, we took a look at how each one failed, taking each under a microscope and applying a code to it, either a brittle edge fracture or a mixed mode edge fracture. You'll see LCY like to break brittly, whereas FSCY prefer the mixed mode. And what we find is that brittle failures tend to yield higher average strengths, as you see below as the results are distributed. Taking our strengths, we applied it into the parametric distributions, and we find an excellent goodness of fit, specifically with the 2-parameter Weibel. Our shape parameters are also very, very low, indicating that we are experiencing brittle failures due to a weakest link effect. This makes sense. We know that with each individual yarn, we get a magnifying effect or a greater amount of defects. LCY being a standard product, least amount. SCY being a separated variation, we introduce surface defects. And lastly, with the FSCY, recent studies show that the amorphous carbon within, when highly compressed, can technically act as little velcros, which can help load transfer. However, they can also be defects. So, what we find, alignments are a governing factor, defects are to blame for our brittle behavior, and we can still technically make some improvements for increasing load transfer. Now, the importance of the work, though, because we are very engineering driven in this case, is the fact that all of this data was provided back to our industry partner, which helped further improve tensile properties when the second generation of these yarns came out. Additionally, we provided a proof of concept to try to both keep our high degree of alignment and try to improve packing, so that way we could potentially get rid of that S-tail phenomena and go directly into elastic properties. Next study, our wettability for interfacing. Wettability data at this moment in time is extremely limited for carbon nanotube yard technologies. In fact, the only study out there that really does it with regards to how we did it, that is by dynamic contact angle tensiometry, really only looked at electrolyte compatibility. We know also from the carbon fiber industry that surface conditions of the fiber greatly affect interfacial strength. So we wanted to take a look how different potential treatment methods that are very popular could potentially affect the yarns. And as I just mentioned, we used contact angles to assist our understanding of chemical compatibility of the carbon nanotube yarns and some select resins that are very popular. If you're unfamiliar with the concept of free surface energy, the illustration below does a very, very good job. The surface of a material can be really kind of comprised of two different kinds of free surface energy, disperse and polar. The closer your matching ratio, the better compatibility you'll have, and therefore the better your interfacial strength should be. So for dynamic contact angle tensiometry, we tested all of our materials in a solid form. That is, we cured out our resins, and the two resins we chose to test in this case was Cytec Solvay's Cycom 977-3 toughened epoxy and 5250-4 RTM bismaleimide. These two were selected because they're extremely popular in the aerospace field, and realistically, carbon nanotubes will most likely buy their way into that industry first. The wetting materials that we used today were deionized water, ethylene glycol, and diatomethane, because they provide us extremes on the end of polar and disperse testing, as well as a good middle ground, while maintaining a high overall total free surface energy. The carbon nanotube yarns that we used today were the single form variant. We tested a neat as received variant. We then tested a heat treated, and lastly a heat plus acid, as seen as A, B, and C below. To test, we used the DCAT system, or DCAT-25 system from Data Physics. The beauty of this particular system, as compared to other studies, is the fact that it is able to avoid complications of non-two-dimensional surfaces. Our yarns are expected to be cylindrical in nature, and as they go in, if you were to do a more static test that's been used in the past, the droplet might roll off. So this can overcome it. Additionally, the way that we are able to obtain our disperse and polar components from this is by using Owen-Wendt plots. After we have tested our 3 points, being our ethylene glycol, diatomethane, and distilled water, or deionized water, we can get our y-intercept and our slope. This provides us our polar and disperse component. Lastly, part of the importance of doing this study is to get our potential wetting parameters. The goal behind this is to try to improve our interfacial strength. So the generalized rule is maximize your work of adhesion, maximize your wetting tension, while at least having a positive spreading coefficient. If it's positive, you are anticipated to have instantaneous wetting. The governing equations are on the right-hand side. Surface analysis of the treatments. Now on to the results. It's pretty well known that functionalization of your surface should increase your total defects. And by doing Raman spectroscopy, we anticipated to see an increasing D-band to G-band ratio. That is, that you have some more, or that you're basically getting more defects at the surface by doing, or when you measure that. However, we saw the opposite. In fact, the untreated had the highest, whereas the fully treated system, all the way to heat plus acid, had the lowest. And we actually used this and anticipated and provided feedback back to our industry partner that potentially there was some sort of residual on the surface. And this is kind of important. And the reason being, if there's something on the surface, it could potentially be preventing resin from infiltrating in. Think of it as a stopper, or you have a traffic jam on these potential channels into your yarn system, therefore reducing the overall potential load transfer that we can achieve. Now this will come into play not necessarily in the 3 studies I showed today, but in the future, or in the final slide where I kind of show you where we end up. So the big takeaway, surface defects were reduced with each treatment. Polar and disperse surface free energy component analysis. We then used Owen-Wentz theory with the DCAT results, dynamic contact angle tensiometry, to get our polar disperse ratios. On the right hand side, you'll actually see those, and I've given us the liberty of highlighting those that have similar ratios and therefore we can anticipate to be compatible. That is, getting a very good degree of adhesion between the two of them. And we see that the untreated carbon nanotube yarns actually should show some sort of compatibility with our 977-3 toughened epoxy. This is important. This will come into play in the final study. So please remember this. And also, interestingly enough, peak. So the reason I chose to include this today is with thermoplastic really taking form in the industry as a potential future evolution in matrix selection, it's good to see at the very least that there is a fiber that could potentially match hand in hand with it. So that's more of a fun little fact for today. Results of the wettability analysis. Now, if you remember, we want our work of adhesion to be maximized, as well as our surface tension, while simultaneously just having a positive spreading coefficient. Well, that doesn't really exist in anything. Those three criteria don't exist in anything but the heated sample. However, the heated sample did not show good polar disperse components, so we can't expect it to want to jive per se. However, once again, there's always a caveat. The spreading coefficient can oftentimes be overcome through changing the environment in which you process your materials. That is sometimes applying more pressure, which is where an autoclave will come in, once again, later. So the summary of our current findings. The treatments actually reduce the surface defects, which is the exact opposite of what we expected. And as of right now, the popular resin systems don't necessarily show idealized wettability with regards to also polar ratios with the CNTs. However, the SciComm 977-3 is very near criteria and may be the source of good results. The importance of the work is that the current state-of-the-art matrix materials might not necessarily be ideal. However, we now understand what the surface chemistry is, and therefore a polymer specific to carbon nanotube yarns could potentially be developed, or if that surface coating that we had mentioned can be fixed, maybe our properties will change further. Lastly is where we combined everything together. So, if you remember from the beginning, the LCY and the SCY had the best properties. So we really focused in on these for this particular study. We also chose two different materials, that is the BMI and the 977-3 that showed good results. We wanted to address the S-tail phenomena, so we actually created a specialized pre-tensioning mold and bagging protocol that could try to eliminate it to as much as possible. We also autoclaved to try to overcome some of the wettability issues. Lastly, we maintained the capstan testing and fracture analysis technique to see how our mechanical properties had changed. And without going through every single possible combination, let me show you the best of the best. That was our small cross-section yarn, which had a greater degree of pores, if you remember, because of the separation process and the higher degree of surface area with the 977-3 epoxy, as we had predicted due to our improvement in wettability. And as you'll see below, we got some pretty significant improvement in properties. In fact, we got an ultimate tensile strength of 1.7 gigapascals and an elastic modulus of 116 gigapascals, while once again reducing our strain to failure because we were able to remove some of that S-tail phenomena. Without going too far into it, once again, we see the SCY epoxy showed the best results, and all of our strength trends once again agreed with our wettability results. The best we were able to get by improvement over our Neat carbon nanotube yarn system are highlighted in blue. We see an improvement in specific strength from the Neat CNTY in the SCY plus epoxy of approximately 41% with regards to strength, and nearly 70% with regards to modulus. These are not results that we were anticipating, but they are fantastic to see because it does prove a few things, which I will discuss at the end. Failure analysis of the microcomposites. If you remember, we wanted to try to keep things ideally failing more often than not in a brittle mode because it provided the best possible results with regards to strength. However, we did notice that the LCY still tended to favor brittle mode, whereas the SCY began to move more into a mixed mode after infiltration, which makes sense. The resin is not something to follow to parameter Weibull with regards to a low shape value. So in the inclusion of it through infiltration, we're beginning to move away from being an ultra brittle material into more of a quasi-brittle regime. Now this is good for us because it means that, as we saw from the strength values, we're moving away from purely having to rely on entanglement and van der Waals forces to actually getting some load transfer mechanism from the resin itself. So what were our conclusions from all this work? We've tested all 3 different CNT systems, and we developed fundamental microstructure mechanical property relationships at true engineering length scales finally. 2, chemical compatibility was studied, and we found some resin of interest, and we now have an understanding of what the surface of the carbon nanotube yarns that are scalable are, so we can actually begin to design things specifically for them. And lastly, when microcomposites are fabricated, we actually see we get pretty significant improvement in properties. Therefore, it's reasonable to assume that carbon nanotube yarns do truly have a path forward with regards to structural composites, even if it has taken many years for us to get here at this point. Now, without giving the true value, I've provided a circled area on the right-hand side. And what that is supposed to represent is the generalized area of where we were finally able to get our Neat carbon nanotube properties by the end of all of this work. This was a culmination of all the data we were able to gather and provide back with regards to both fundamental science as well as some basis behind engineering. We're very confident that carbon nanotube yarns do actually have a future. I'd like to acknowledge the people who were able to help me fund this research, that is US Comp through NASA, as well as the Florida Space Grant Consortium Fellowship, Huntsman Corporation and SciTech Solvay for providing materials, Dr. Ashley Harden, Eitan Zera for providing information regarding the Miralon product that I worked with, Dr. Rebecca Sweat of Florida State University for her useful discussions regarding carbon nanotubes, as well as my advisor, Dr. Richard Liang, and my entire research group for everything they've been able to do for me. Thank you.